Okay, so we are recording here. Okay, so section 5.10 is on what's called improper integrals. Now, here we have an integral, and what do you think makes this integral improper? Why is that integral, why are we calling it an improper integral? Samuel? Yep.
Because its lower bound is negative infinity.
That's right. Very good. The lower bound for that integral is negative infinity. Okay. There it is. Now, up to now, the definite integrals that you've had have had finite numbers for the limits. But now we come up with a situation where one of our limits is negative infinity. And we're also being asked, does the integral converge or diverge? Well, if an integral, so remember, this integral represents area underneath a curve, right? Area, actually, we could call it area between the function, x times e to the x power, all right, and the x-axis. But one of our bounds, our lower bounds, negative infinity. So if the area is finite, we say the integral converges. If the area is infinite, we say the integral diverges. Okay, so let me show you how we do this problem here. Okay, here's what we got to do. First of all, I draw a picture of x times e to the x. Okay, I draw a picture of x times e to the x. And here is the area here. Here's all the area. And the function, of course, the left limit is negative infinity. So this, maybe I'll use my stylus. This this keeps going, right? The function keeps going. And it gets closer and closer to the axis. I mean, I'm trying to draw it. It's trying to draw it the best I can here. One moment. The function gets closer and closer to the x-axis, okay, as x goes to negative infinity. And the question is, there's always a little bit of area in this tail on towards infinity. But the question is, does the area, does it build up slow enough for the area to be finite? I mean, it's sort of amazing. Most people would think, man, since the function never touches the x-axis and we're always adding more area as we go out, to negative infinity, that area has to be infinite. That area, that integral has to diverge. But in fact, if the area as it's being built up is built up at a slow enough rate, the area actually will be finite. But what we have to do, of course, and then this is by the way what's called a type 1 improper integral, because the bottom limit is negative infinity. That's a type 1 improper integral. Okay, so what the integration techniques you've learned were in terms of proper integrals, where the bottom and top limits were finite values. So what we're going to do, what we're going to do to handle this is we're going to consider a proper integral that has a finite upper limit of 0 and finite lower limit of t. But we're going to let t go to negative infinity, and we're going to take the limit. So what we're going to be doing is we're going to be computing this definite integral here, okay, using the techniques that we've learned. And then once we get the antiderivative, okay, and substitute in t and 0, then we're going to take the limit. So clearly, this is a type. This here is going to be, well, what am I doing here? What approach am I doing here? I'm letting u equals x and dv equals e to the x dx. What approach is that? Samuel?
Integration by parts.
Integration by parts. Okay, so integration by parts. Okay, that's what we do. And so our, yeah, let me see here. Hold on here, one moment. We have the integral of u dv equals uv minus the integral of v du. Okay. All right, that's our integration by parts, and so I apply that here. Okay, are there any questions up to this point right here?
Professor?
Okay. Yes.
What's the difference between convergent and divergent integrals?
Convergent means convergent integrals mean that the convergent integrals are ones that have finite area. Divergent integrals are improper integrals whose area is either infinite or it can't be determined. Converge means to come together, right? Like finite area. Diverge means to, not come together, go to infinity or negative infinity. Good question, good question. So you notice in this problem, I keep the limit all the way through the problem. So I'm doing the integration. I'm doing the integration by parts here, and I'm substituting in. I substitute in the 0 and the t limits, but I still keep my limit here. Okay, so down at this step here, down here, right here. Okay. As t goes to negative infinity, what does this e to the tth power go to? As t, I mean, what is e to the negative infinity equal to? That equals 1 over e to the positive infinity, right? Okay, e to the negative infinity equals e to the 1 over the positive infinity. What would that equal? E to the infinity.
0.
Yeah, e to the infinity is like taking e and raising it to a very high power, right? It's huge, a huge number, right? I mean, if you have like e to the 100th power, try that on your calculator. It's not even going to give you an answer. The calculator probably won't be able to handle that. I'll try it right now. It might give something. Yeah, you know what e to the 100th power is? E to the 100th power, according to my calculator here, my TI-84 calculator, e to the 100th power is equal to 2.0 68 times 10 to the 43rd power. Okay, a huge number, right? So e to the t, this goes to 0. And what's e to the 0th power? What's that equal? What's that equal? E to the 0th power is equal to 1. Okay. So this part of the limit and this part of the limit is no problem. No problem. Now we have to worry about the t times e to the t. So, well, actually, hold on. I'll look at the whole thing here. One moment. Let me see here. Do I want to look at the whole thing? Let me see. Yeah, I'll just look at t times e to the t. So t goes to negative infinity. So we're taking negative infinity and we're multiplying it by e to the negative infinity. Right? You learn this from your section 4.5 exercises, L'Hopital's rule. This is indeterminate form, right? You have e to the negative infinity times 0. Okay. What kind of form is that called? Is negative infinity times 0 necessarily equal to 0?
Isn't that an indeterminate form?
That's right, Maria. It's an indeterminate form. Oh, what do we have to use to get that? To compute that? What do we have to use?
L'Hopital's rule.
Good, L'Hopital's rule, and that's why we had to cover section 4.5, L'Hopital's rule. That's why we had to cover that. Okay, so let's go to the next page.
Wait, Professor. So, why would that be indeterminate if it's negative infinity times 0?
Well, you have one term that's getting bigger in a sense. I mean, it's getting very negative, and then you're multiplying that by another term that's going to 0. So it's like you have something getting bigger times something getting smaller. We don't know if that goes to infinity. We don't know if that goes to 0. We don't know if that levels out to be a constant. It really depends on the rate at which t goes to negative infinity and the rate at which e to the t goes to 0. That determines really the limit. And this is where Marcus de L'Hopital's rule comes in. So you see that t times e to the t there. What I do is I say, okay, well, I can't use L'Hopital's rule on this right now because the indeterminate form, let me use my...
Can I ask a quick question? Can you go back to the previous slide?
Sure.
So at the bottom, you said that it was going to be negative infinity times 0, but wouldn't that negative make it positive infinity times 0?
Well, you could think of it like that. I wanted to kind of keep the negative, I didn't want to worry about it, but sure, you could treat it like this.
Okay. I was just trying to clarify. Thank you.
No problem. All right, very good. So I just kind of focus on this part here. I'll bring that negative in later. And so I have here negative infinity times 0. Okay, but I know I can't use L'Hopital's rule on that indeterminate form. L'Hopital's rule is used when indeterminate form would be like infinity over infinity, negative infinity over negative infinity, or 0 over 0, right? Those are the indeterminate forms for L'Hopital's rule. So I have to rewrite this as t over e to the negative t. Okay, I have to rewrite it like that. And when I do that, I have now a numerator. I have a numerator that is going to negative infinity, Well, I mean, this we can also use L'Hopital's rule on that. I guess technically L'Hopital's rule, you can have plus or minus infinity over plus or minus infinity. That's fine. So it's indeterminate form. The numerator goes to negative infinity as t goes to negative infinity, and the denominator goes to positive infinity. Because if you have e to the negative infinity, that's the same as e to the positive infinity. And so we can use L'Hopital's rule on that. And that means we take the derivative of the numerator and the denominator. And now we look at the limit as t goes to infinity of the ratio of the denominators. Okay, so you have here, hold on here, you have an f over a g, and this would be an f prime then over a g prime. And so you're going to get 0 for that, because 1 over infinity is 0, because the denominator, or 1 over, well, this really approaches right 1 over negative infinity, and there's nothing indeterminate about that. That equals 0. So now I'm able to, my integral now is this limit, the limit of this function of t, and the limit of this function of t would be the sum of the 3 limits. And so I break the limit of that function of t into the sum of the 3 limits, and that gets me -1. So we knew based on the picture, I'll just show this real quick, I'll pop back on this. Based on the picture, right, all the area is below the x-axis. So the area has to be negative area. And so turns out that we get -1. And so that means our integral converges. And I'll show this on the next page. I'll be a little more formal about that. But are there any questions so far? Yes, Marcus.
So how did t turn to 1?
How did, I'm sorry, you mean, are you looking here? You're looking here?
I'm looking, could you see my pointer thing?
Oh, here? This?
Yeah.
This is L'Hopital's rule, section 4.5.
Oh, right. Wait, so how did you go from -t e to the power of t minus 1 plus et to just t e over t, or t to the power of t right here?
How did I go from here to here?
From
So
this one to this one.
well, all right. What I'm doing is I'm very comfortable. Good question. Good question. I mean, -1's no problem. That the limit doesn't affect that. And e to the t power, that's going to go to 0 as t goes to infinity, negative infinity, I should say. So the only thing I have to worry about finding the limit for, the only thing I'm uncertain about is this function here. And I'm going to leave the negative off, okay? So the only thing I'm uncertain about in finding this limit is t times e to the t. And so that's why I'm doing that separately here using the L'Hopital's rule. Then when I put that h over the equal sign, that means I'm using the L'Hopital's rule. And so it turns out that limit equals 0. So basically the limit's going to be 0 minus 1 plus 0, right? That's going to be the limit. After I take the limit of this entire function of t, it's going to be 0 minus 1 plus 0. And
So
that's what I have. That's
It-
what I have here.
It wouldn't have mattered if you did do negative t to e
It-
times
it-
e to the t or t times e to the t. You're going to get
That's
0 either
correct.
way.
It would not have mattered.
Okay.
That's correct.
So that helps,
Nathan?
Marcus?
Yeah, yeah.
You said what?
Good. All right. Marcus, you're good? You're comfortable?
Oh, not really, but it's okay.
You're more
Thank you.
comfortable, right? You're more comfortable. All right. We'll go with that for now. Remember,
Okay.
class, after our class, I always stay a little bit to if there are any follow-up questions. Okay. I want you to be successful. I want you to be comfortable. Nathan, you had a question?
Yeah, I guess conceptually, I don't understand how the area under the curve can be -1 when the graph never crosses or touches the x-axis a second time.
That's right. You're like here, yeah. We know the area is negative, but how can it be that the area keeps building right onto infinity because the graph x times e to the x never touches the x-axis? You're right on that. But in fact, the truth is the truth is the truth is the truth. And if I write, writing this integral here as the limit of this integral is certainly allowed, right? That we can certainly do that. And when I took the limit, I ended up getting a -1. So it's something that absolutely, it's something that many, probably 90% of the people in the world don't know this. They have to take calculus too. It's probably even less than that. It's probably even more than 90%. But in fact, it has to. It is a concept that is sort of strange, isn't it? But it is in fact true. It is in fact true because it's like it. Well, I want you to sort. I'll tell you what. We'll do another example, and let's see if you feel a little more comfortable with it. Okay. I think you see another example. It'll certainly help. So can I keep you in suspense a little longer?
Yep.
All right. Good. 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 Let's see here. I'm going to go to the next page. Are there any other good questions? Okay, let's move on to the next page. So this integral equals -1. And so we say the integral converges. It converges because our limit exists and it's a finite number. And we call this improper integral an improper integral, a type 1 improper integral. Whenever you have one of the limits as -infinity or positive infinity, it's called a type 1 improper integral.
Okay, so I have a question. It might seem like a silly question, but based on what you said about the graphing calculator or the scientific calculator, that we could only use that part of it on Desmos.
Correct.
At the beginning of this problem, you graphed the function to see if it was something that we needed to evaluate.
No, I just the only reason I graphed it is so that you could. The only reason I graphed it is because I just wanted to show you a picture and show you that the area never stops.
Right, but are you ever going to need to graph it first, or are you expected to evaluate it to determine whether or not it will?
That's something I was thinking also about looking into.
Mm-hmm.
Certainly for part 1 of the exam, the Desmos calculator you have should be adequate. But if I can find another version that can do the graphing but not have that integral feature, on it. I'll definitely make it available. I haven't been able to find it yet, Maria,
Right.
but I'll look into it. I'll make
That's
a
okay.
note.
I was just wondering because the way that you worded the question on the first slide, if you can
Yeah,
go
I had
back
a
to that
picture,
first
didn't I?
slide, it said,
Yeah.
no, before the first slide,
Oh, okay. Yeah,
you
yeah.
said, does it converge or diverge? If it converges, evaluate it. But you wouldn't know whether or not it converges or diverges unless you actually see a graph. Am I correct?
Oh no, I don't. This graph is just for illustrative purposes. No,
So
no,
you
I
do,
don't.
so you
I
do
can
need to evaluate it to determine whether or not
correct.
it's converged. Okay. So the wording was
Yeah,
just, the
that's
wording
fine.
was confusing me. Thank you.
No problem. Good question. Good question. Okay. Okay. All right. Are there any other good questions before we move to our next example? Okay. Well, let's look at another situation here. Let me give you a moment to copy this example down. Okay, so this integral, well, now this integral, we do have finite limits, 2 and 5, or fine, you know what I mean, the number on the bottom, the top, yeah, the limits are finite. But yet, this is an improper integral. What's the problem here? Why is this an improper integral instead of a proper integral?
Is it not continuous?
Where is it not continuous, Samuel or Nathan? What I think was it Nathan who said that. Nathan.
Yeah.
Yeah. Where's it not continuous?
X equals 2.
That's right. Exactly right. Our function is 1 over the square root of x minus 2. But the domain of this function is what? What's the domain? X has to be what? Then you have a square root in the bottom. What's the domain?
Greater than 2.
Good, greater than 2. That's right, Jacob. That's right, Samuel. That's right. I believe it was Maria. That's right. X is greater than 2. So at x equals 2, this function is going to have an asymptote. Okay, and when you have an asymptote, you build up area at the asymptote. So if we look at a picture here, and again, this picture is just for illustrative purposes, is the area finite? Okay, here you got this function, it equals 1 over the square root of x minus 2. And this is a graph of it. And, that's a graph, okay? And here's the area. And now the area is building up here, where at the asymptote of x equals 2. Okay, that's where the area is building. Okay, and so the question is this area finite or not? This type of integral is called a type 2 improper integral, type 2. So again, what we do is our integration techniques are in terms of proper integrals. So what I'll do is I'll replace the 2 here at the bottom, that bottom limit, I'll replace that with the t. I'll leave the 5 where it is. 5 isn't causing any problem. I'll replace the 2 with the t. Okay, and then I'm gonna compute this integral, this definite integral, and then take the limit as t approaches 2, but as it approaches 2 from the right side, right? Because we're approaching 2 from the right side. How many remember one-sided limits from Calculus 1, those one-sided limits that you had to compute with the, okay, Sean remembers them. Jazi remembers them. Okay, who can forget them, right? Well, all right, so clearly here, substitution is the way to go. Samuel, question?
Wait, hold on. So this is a one-sided limit right over here.
It's a right-sided limit. That's correct, because
Oh wait, that's not. Oh, that's. I see. I was mixing it up for a plus sign, not a from the right side.
well, the plus, yeah, oh, okay, yeah, the plus is like a superscript.
My mistake.
No problem, no problem. Okay, so I'm going to let u equals x minus 2, du equals dx. Okay, all right, and now I convert this integral with respect to x into an integral with respect to u. The u limits, the x limits now get changed, of course. The 5 becomes a 3 because, well, u is equal to x minus 2, right? So 5 minus 2 is 3. And then the bottom limit becomes a t minus 2 because u is t minus 2, right? And so now I move forward to compute this integral. And notice I keep the limit all the time. I keep the limit there. It's not hurting anybody, and it makes the work look good. You know, sometimes students like to compute the integrals separate and then bring the limit in later, but it's usually not good. You know, it's not the right way to do it. You want to. This is when you find an improper integral, you are doing a limit problem. You're doing a limit problem, and you are experts now on limits, having taken Calculus 1 and knowing L'Hopital's rule. All right, so please let me know if you have any questions before I go to the next page. All right, may I go to the next page? Maybe give me a thumbs up if you're ready. Nicole's good, Tal's good. Okay, very good. All right, let's go forward. Thank you, everybody. Then that helps because I can, of course, you know, if I were in a classroom, I could see that you're all ready to go to the next page. So that helps. Okay, so continuing on here, I'm gonna, you know, here's my limit. The antiderivative, by the way, of u to the negative half is equal to 2 times u to the positive half. And I got limits of 3 and t minus 2, and I'm going to feed them in. And then I'm going to take the limit at the end. As t approaches 2 from the right, this is going to approach square root of 2 minus 2, which is square root of 0. Okay. Okay, and so we get the 2 root of 3 as our answer. And so therefore the integral converges, and that's its area. Absolutely amazing. Absolutely amazing. Now, if the integral diverged, we would have what as an answer? If the integral were a divergent integral, what would our answer be?
Infinity.
Infinity. Okay, but those aren't very interesting. And these improper integrals are important. Like, for instance, if you wanted to compute the mean life of an atom, okay, in physics, that involves an improper integral. If you want to determine Laplace transforms, if you take differential equations, Math 282, you'll have Laplace transforms. Those are based on improper integrals. So it's a really important concept. Okay, are there any questions? I'll do some more examples here. So I think we're just going to try to do examples, and then we'll kind of naturally end the class a little early. The assignment for 5.10, I need to get it posted. You're worried about the exam now, but I'll get it posted. The assignment for section 5.10. Well, let me just do a stop on the recording here.